see if we can get the idea of alignment and roll a quick rehash in sub 10 minutes. So the idea is I've got some little bit of a line that I'm calling C. It could be curvy, but let me just go with the idea that it's straight for a second.
Is that a vector, C?
So C is a path, and really all the path means is it's the idea of a curve in space. I don't have a formula for it, I don't have anything to do with it when I just have a C. Right, it's just the idea. Then I could look at this C, and maybe if I've got my brains right and the stars align, I might be able to come up with a nice parameterization. Some function R of t, right? And that thing traverses C from end to end. So over here on C, there's some point A and some point B. Maybe let me try to label this with a little bit of color. So if we make that R of t, right? We've got the idea of a curve, that's the black thing. Then I've got that kind of execution of this curve, which is a red thing. And this thing says, okay, when I'm looking at A, that happens at some time. And I've got B, and that happens at some time. Oh, and I should probably give this curve a direction. So let me just say for simplicity that it goes from A to B. Cool. Just good with this?
Is A always equal to T, or could it be all different scales?
Yeah, of course you could change the scale on this. We could of course come up with a different parameterization for this, right? And we should get the same answer out of the line integral. So this is just the kind of setup with the curve. In the background here, laying in R2 someplace, there's a vector field. And that vector field might look like this. For simplicity, I'm kind of drawing a relatively constant vector field, right? If I want to know how much I get helped by this flow going from A to B along C, right? I just want to know, hey, like when you start out, how much help is this thing giving you? Oh, that one's a little bit off. So to put it along the others, right? Well, it's not totally perpendicular, right? It's not pushing against me, it's helping a little bit. I gotta figure out how much. So I'm gonna take a point, right? That starting point, say, and I'm gonna say, okay, how much am I getting helped right there? So I'm gonna think to myself, okay, when we first start, right, at T is A, there's some vector field happening there, right? That's F. That's the force. But F's supposed to take X and Y's, right? So really what I want to do is evaluate F at A.
So that's a better way to look at it, is thinking that F is force, not so much
Yeah,
okay.
yeah, F is a vector field.
I was thinking the antiderivative, because they use the big F too.
Oh yeah, yeah, it's not the antiderivative thing, necessarily. So let me think here. So what I've got is I've got a point that I started, I've got some flow going past me, right? And I've got some direction I want to go in. I want to know how much does the flow there, right, this bit, that's my blue arrow. How much does that thing agree with the idea of moving along C, right? Can you see that? So right at the beginning there, how am I moving along C? Well, C is just the idea of something, right? It doesn't have any moving along. So to get an idea of moving along, I think about that red thing. I think, okay, there's some arrow there. That's happening in an instant, right? You guys see that? So I really want to say, okay, I'm going to take my F and I'm going to dot it with some kind of little change in R. I could do a little better than this, but let me start with change in R for now. See that? And really I'm thinking this change in R, this is happening at A. Take my log now. Okay, so I've got my vector from the field. My vector I want to go along. I want to know how much they agree, so I dot product them together.
Okay, so you're dot producting the force times the vector.
Yeah, I'm dot producting the force times the direction I want to go in, more or less. Right? That's going to tell me roughly how much they agree. There's going to be some kind of magnitudes involved there, right? But roughly this thing's going to be, so if I think about this whole deal, this whole business, that's going to give me magnitude of the force times the magnitude of the change in direction, or the change in position, right? Times what? Perfect. Cosine of the angle between them. So if I kind of hold my hand over the force and the change in direction, really what I'm talking about is how much do these two things agree on a scale of -1 to 1. Right? -1 being they point in opposite directions, 1 being they point in the same direction, 0 being they're perpendicular. You can see how that more or less gives me how much this is going to kind of push me along. This is kind of how much wind is at your back, right? But that's just for the point T is A, right? So that's just right here. Well, what I'd really like to do is kind of chunk this thing up into a bunch of pieces, right? So I say, all right, I'm going to chunk this thing into several pieces. I'm going to get a little red delta R vector for each piece. I'm going to get a little blue force vector for each piece. And then what am I going to do to get the total help? Yeah, I'm going to add them up. So first things first, I'm going to go, all right, total. We're going to sum up these stuff like this. F at someplace times the change in R. So where's the someplace I need to evaluate these?
R and T.
Yeah. I need an XY pair, right? So I want to know when is this thing happening, right? There's some dot here. There's a force there and an R there. That's happening at some time, right? Maybe some special time, right? But what's the two-dimensional coordinates of that? I got to get them out of putting them into the function R. Does that make sense?
Mm-hmm.
So I run that special time, put it in my parameterization, and then I put the result of that into your function F. So this thing's a Riemann sum then. So of course we want to limit on taking the delta R's to 0. Right,
So by that one, you're timesing it by the, or you're taking the RT timesing the derivative of RT.
yeah, so when I take the limit of this, right, I get the integral of F dotted with dr. But then to execute this, right? So that again is an idea, like C was the idea of a path. But the execution of it is you need to know, all right, we're gonna give ourselves some times, some A and B, right? And then we're gonna evaluate F at R of T. And we're gonna dot product with R prime of T. Right, that's our instantaneous red arrow instead of our average red arrow. And then we need to integrate this
dt.
dt, because it's kind of the only choice you've got. Does that kind of make sense?
Mm-hmm. The only thing I think that might be a little confusing, maybe I was just reading it wrong. We were working with, I was doing a couple of the early ones on 18.2.
Okay.
And they were doing cause and sines. And they switched the places of the IUJs based on when it turned to sine and cause. And that was, it kind of made sense, but if you, like cause you think would go with i's.
Okay, yeah, so once they take the derivative, right, they switch
Mhm.
places?
Yeah, they switch the i's and j's on opposite, so they go with the cause is i's and the signs are j's.
It's because there's a Y with the eyes, I think.
Yeah, so on that one specifically, the vector field that they're talking about is yi plus xj. And so they get switched in spots. That's, you have to be really careful evaluating this thing.
Yeah.
Those are, yeah, this is probably the hardest step. Getting R prime is easy, taking a dot product is pretty chill, you guys are all pretty good at that. It's gonna be this thing, where you take that vector field and evaluate it, your parameterization, it's gonna be tough. The other thing, of course, that's a little bit hard here is conjuring that parameterization out
Mhm.
somewhere. Other questions? I catch up about Ryder?